So we're going to talk about different ways to combine functions today. We can create new functions by combining two or more functions through one of the four operations of arithmetic. You can add, subtract, multiply, or divide functions. Right? So this is just some different notation for adding, subtracting, multiplying, and dividing functions. You can either write f plus g and then an x, or f of x plus g of x. They mean the same thing. And the domain of two functions that are combined via standard arithmetic is the intersection of the domain of f and the domain of g. So let's do an example here. So if we let f be the function x squared and g be the function 1 over x plus 1, what's the domain of f? You got it. Yep. Negative infinity to positive infinity. You can plug any x value you want into x squared. There are no restrictions. If you look at its graph, it would live on all of the x values. So if I was going to graph the domain of f, right, it would just be, I would just be highlighting the entire real line, right? That's its domain. All real numbers, negative infinity to infinity. All right, and then let's look at g. What's the domain of g? 1 over x plus 1. All real numbers except for negative 1. So if I was going to do that in interval notation, I would say negative infinity to 1, not including the 1 because I can't put 1 in, and then union that with 1 to infinity, right? Not including the 1 in either of these. So that is just one way of writing all real numbers except for 1. So if I was going to graph that one, do it in a different color. Here's 1. I'm going to put a hole there because I can't put that in, and highlight everything else. So that's how I would draw a picture of all real numbers except for 1, the domain of g. All right, and then the intersection of the domain of f and the domain of g, that is all the points that the domain of f and the domain of g have in common. What is the intersection of those two domains? Where do they overlap? All values except negative 1. Or 1. Negative 1. Negative 1. Thank you. They overlap at all values of negative except for negative 1. They don't share negative 1 because negative 1 is in f, but it's not in g. So they don't share that. So the overlap of their domains is this guy. So all four of these functions, f plus g, f minus g, f times g, f over g, they all have the domain, the intersection of f with the intersection of g. The intersection of f with g. Okay, so if I want to add two functions, f plus g, just add their formulas. Done. If I want to subtract two functions, subtract their formulas. Done. Multiply two functions, multiply their formulas. And then I suppose I could write that that equals x squared over x plus 1. Quick simplification. The addition and subtraction, I could get a common denominator and add those together. You don't have to. Just leave it like that. And then f over g, just divide their formulas. X squared divided by 1 over x plus 1. And I would simplify that to x squared times the reciprocal, x plus 1 over 1, which is x cubed plus x squared. Pretty straightforward, right? This is just all simplifying expressions that you've done before. It's just that now we've named these expressions f and g. Okay, so for composing functions, this is a fifth way that we can combine functions. Other than addition, subtraction, multiplication, division, we can compose functions. Composing means using the output from one function as the input for the next function. So for example, let's define two functions, m and f. The m function we'll call the mother function, and m of p represents the biological mother of person p. And the function f we'll call the father function, and f of p represents the biological father of person p. So what do you think m of f of p is referring to? Grandparent, yeah. Because f of p means the father of person p. Father of p, right? But then m of something means the mother of that person, right? So this is the mother of the father of person p. We call that the paternal grandmother. Right? Your grandmother on your father's side is your paternal grandmother. Yeah. Oh, yeah. So F means father, right? So P is the person. F of P represents their father. And then M of F of P is the mother of the father of the person, which is the grandmother on the father's side. So visually, we have person P, right? Is the input. That's the very first input. And then we apply function F and we get F of P, which is the father. So this is the original person. And then we have P's father. And then you apply M to P's father, which is the mother of that person. So this is M of F of P, right? This is P's grandmother. So you read M parentheses F parentheses P as M of F of P, and we call that function the composition of M with F, or just the composite function. Often it's written with this little circle, M little circle F, or like that, and it just means with the same thing that the parentheses mean. So when you see the little circle, just translate it to using the parentheses. I think it's much clearer.
Yeah, how does that equal?
This is just a brand new notation. That's not a dot, it's a little circle, right? So versus the dot, right? Dot would mean multiplication, but that just means composed with, right? So this is, we're defining this new thing to mean this. Why? I don't know, it's stupid. We have a perfectly good notation that means that. I don't know why we need a new one. Composed with? Oh, I don't know.
Is in this new composition?
Yeah.
Is the first term on the outside of the parentheses always? The second term?
That is a great question. So with composition, you always work from the inside out, right? So this is your, like, P is your input, and then you take the father of that person and then the mother of that person.
Right.
Yeah.
But the new.
Yes. So yeah. So if I wrote F circle G, right? That would mean F of G of X. Yep. Okay, so the question is, does the order matter? What if I switch the order here? Instead of doing M of F of P, I did F of M of P. Who does that refer to? The maternal grandfather. Yeah, so different person, right? So this is the maternal grandfather. right? The father of the mother of person P. So your mom's dad is your maternal grandfather. So the way we look at this, we would put person P in here, right? And then their mother is M of P. And then you look at the father of that person, so that would be the grandfather. So here's my definition for composition of functions. Composition of a function f with g is denoted by f circle g, and it's defined by f parentheses g parentheses x, f of g of x. So like I said, whenever you see this little circle notation, just rewrite it with the parentheses. It's much clearer about what it means. The domain of the composite function is the set of all x's such that x is in the domain of g, right? Because you work from the inside out. So you have to be able to put x into g, and then you have to be able to put g into f. So you have to consider both functions. So we'll do an example in right now. Okay, so I've got two functions, x squared and 1 over x plus 1. So if I want to evaluate f of g of 3, that means f of g of 3. That f circle g just means f of g of 3. So you work from the inside out. So if you look at that 3 and you say, okay, the first thing I'm going to plug 3 into is g. What do you get when you plug a 3 into g? 1/4. Okay. So I'm going to replace g of 3 with the value that it's equal to, right? G of 3 is 1/4. So my next step, I'm going to do f of make a substitution, replace g of 3 with what it equals 1/4. And then what is f of 1/4? 1/16. So think of this as like two successive machines. I've got the G machine and then the F machine. So I'm going to draw this out here. So here's G and F. So I'm going to put a 3 into the G machine. Okay. And you turn the crank, and G takes that 3 and turns it into a 1/4, output of 1/4. Right? Then you take that 1/4 and you take the output from G and drop it into F. Turn the crank, and F changes that 1/4 into a 1/16. So this is the composition of two functions. If you have, consider each of those functions a machine, and you run them in succession. All right, so let's think about G composed with F of 3. So this means G of F of 3. So we're reversing the order of the machines here. The first machine is going to be F, and the second machine is going to be G. 3 goes into F first, so I'll draw a little picture. So this time F is the first machine, and G is the next machine. And I'm going to put a 3 in, and turn the crank on the F machine. You put a 3 in, you turn the crank. What does F turn 3 into? 9. Okay, then you take that result, that 9, and you plug that into G, and what does G do to 9? It makes it a 1/10. So G of F of 3, using pictures, you get a 10th. If I want to use my standard notation, I would say, well, first thing I do is if I evaluate F of 3, and I make a substitution, replace F of 3 with what it equals, which is 9, then plug 9 into G, and you get 1/10. All right, so let's suppose I want to write a formula rather than having to use two successive machines. Maybe I have a company and I don't want to have to take the result of one machine and put it into the next. I just want to have one machine that does the whole thing, right? That will turn 3 into 1/16 and will turn, which one am I doing? F composed with G of X. Yeah, that will turn 3 into 1/16 without an intermediate step. right? I just want to have one machine, one formula that will do that. So if I want to find f of g of x, one formula. So what is the formula for g of x? Yeah, just, and g is 1 over x plus 1, right? Okay, so I want to apply the function g to x first. So when I plug in x into g, what I get is 1 over x plus 1. So I'm just making a substitution. G of x is equal to this formula. Replace g of x with what it equals. Substitution. Okay. And then what does it mean to do f of 1 over x plus 1? What does that mean? No, it does not mean multiply. This is function notation. Square it. Yeah.
Oh, okay.
F is the function that squares stuff. So just as a little aside here, if f of x equals x squared, then f of 7, right, means 7 squared, right? F of a picture of a little house means picture of a little house squared, right? Whatever you put into f, it just gets squared. It's just a machine that squares things. So when I put in a 1 over x plus 1, f is the machine that squares things, so I'm going to get 1 over x plus 1 squared. And I could draw a picture of how this is working. So this is my formula. And we could just check. If you put a 3 into this function, what do you get? Close. 1/16. Yep, because 3 plus 1 is 4. So this is 1/4 squared is 1/16. And that's what we got when we did it in 2 steps. So you can check that your formula works. Right, because f means square it. So we just wrote that, we just squared it instead of writing f. Yep. So what is the domain of f composed with g? So I'm going to draw some pictures here. G is the first function. F is the second function. So G was 1 over x plus 1, right? And F is x squared. Okay. What kinds of x's can I drop into the G machine without causing the machine to break down? Anything but -1, right? So in here, I can put all reals except x equals -1. And then do I have any restrictions on f? Anything that I can't put in the f machine? No. Whatever comes out of G, I can put it into f because f is the machine that squares things, and you can square anything, right? You can't divide by anything, right? Because you can't divide by 0, but you can square anything. So there's no restrictions on machine number 2. My only restriction is on machine number 1. So my domain is -∞ to -1, union -1 to infinity. Just all reals except for -1. All right, let's do the reverse order. Let's do a general expression for G composed with F. Okay, so this is G of F of X. What's my formula for F of X? X squared. So I'm just going to make a substitution. I'm going to replace F of X with its formula, right? So F of X is the same thing as X squared. So I replace this. This becomes G of X squared. All right, and then that means plug x squared into the formula for G. All the x's in the formula for G get replaced with x squareds, and the formula for G was x plus 1, so it's x squared plus 1. Does that make sense? Let's see if it gives us the same result as the successive machines. The successive machine says if you plug in a 3, you should get a 1/10. If I plug 3 into this formula, what do I get? 1/10. Okay, so that formula makes sense. All right, so if I want to find the domain of this thing, I like to always draw pictures when I'm doing domains of compositions because it can get a little tricky, as we will see in this example. So this time, F is the first machine and G is second. So the first thing that goes in is X. It goes into the F machine. Any restrictions? No. So no restrictions here. I can square any X I want. But then what comes out here is an X squared, right? You put in an X, you get an X squared. You take that X squared and drop it into G where there are restrictions, right? What can I not put into G? -1. So X squared can never be -1, right? What I get out of F can't be -1 or I'll break the G machine. Okay, but are there any X values that would give you a -1 when you square it? This never happens, so I'm fine, right? So I don't have to ever worry about getting a -1 out of the F machine. You can't ever get a -1 out, so I'll never jam the G machine. So my domain is actually all real numbers. I can plug any number I want into the composition, but because it goes into F first, and F will square it, ensuring that I never jam the G machine. All right, you try.